So now we move to fundamental principles that allow us to check the admissibility of constitutive models. So the first one is the principle of material frame indifference, which is also called objectivity. So the basic idea behind this principle of objectivity is that the constitutive equations that we develop to relate the responses such as stresses with causes such as strains should not be dependent on the observer who is making the measurements, because it is a property of the material, not a property of the observer. So when we say observer, the observer in the spatial coordinate system could be translating or rotating with respect to the current configuration. So that information about the observer's movement should not be reflected in the stresses that we calculate, because the stresses are purely functions of the deformation in the material, not a function of the observer. Let us start with an example. So we have a viscous fluid, as we discussed in the examples earlier, and the response, that is stress sigma ij, is given as a function of the rate of deformation or the rate of strain dij, and dij is defined as the symmetric part of the velocity gradient tensor. So this choice of ours to represent sigma in terms of the rate of deformation is an objective choice. So we say that the measure, that is the rate of deformation d, is an objective tensor. On the other hand, if one was to naively propose sigma as a function of the velocity gradient tensor, the choice velocity gradient here would be non-objective, and that's a bad choice. And the reason for that is that if you look at this vi comma j, the velocity gradient tensor, which is written as Lij, it's a sum of dij plus wij. So dij is the symmetric part and wij is the skew symmetric part. And the skew symmetric part has information about rotations or the rate of rotations. So if the observer was rotating, then the rotating observer would end up measuring that as an opposite rotation of the material. So this wij will get modified because of the observer's motion, and that will affect the stress as a result. So the deformation was exactly the same, just the observer rotated, and that resulted in the stress being calculated differently. So there has to be something wrong with this. And that is the reason that we end up choosing measures or quantities which are objective, that is, they do not depend on the rotation or translation of the observer. So this choice D was an objective choice, whereas the choice Vi comma j is a non-objective choice. So whatever models we propose should be able to filter out the motion of the observer from the calculation of the responses such as stresses or heat fluxes. And this is possible if we end up choosing objective tensors and not non-objective tensors in the model. So let us try to understand this idea of objectivity through problems, which will help us understand how to mathematically evaluate whether a measure is objective or not. So let us say that there is a deformation where we go from a reference configuration to a current configuration in the body. This coordinate system O small x1, small x2, small x3 is the coordinate system that is used to measure the deformation in the current configuration or the spatial coordinate system. So we have a mapping from capital X to small x, but there is a superposed rigid body motion. So that means that there is an observer at point P which is also rotated. So this is P small x1 prime, small x2 prime and small x3 prime. So this observer sitting at the point P is making the measurement, not the observer who was sitting at O. So we call it as a superposed rigid body motion, where the measurements by the rotated observer are given as xi prime as aijxj plus ci, where ci has the information about translation and aij is our rotation tensor, which is orthogonal tensor. So this has the information about the rotation of the observer. Now the question is to check whether we could write our constitutive law in terms of, let us say, f, which is the deformation gradient tensor. So basically we have to check whether the measure f is an objective measure or a non-objective measure. So our FIA is defined as del by del capital XA of small xi, and our F prime IA would be defined as small x prime I by del capital XA. So nothing has changed with capital X. So our reference configuration, which was defined as some O capital X1, capital X2, capital X3 with respect to this coordinate system, that still stays intact. It is our spatial coordinate system that is rotated because of the observer making a measurement in the current configuration. So F prime IA now becomes, because we have a relationship between xi prime and xj, so this becomes aij del xj upon del capital XA, that is aij times fja. So if I were to write this in symbolic notation, this becomes f prime is a times f. So what we notice here is that this f prime that we have measured, it depends on a. If the observer rotated differently, then f prime would be different. So if my constitutive model was written with sigma in terms of f, then there would be something wrong there, because of the rotation of the observer, or as we call it sometimes, the superposed rigid body motion, the stress calculated would be different, which is incorrect. So we say that since f prime depends on a, f prime is non-objective or it is not objective. So if f is not objective, then let us see if the quantity c, that is the Green's deformation tensor, which is f transpose f, if that is objective or not. So again, for evaluating whether c is objective or not, we basically check whether c prime is a function of a or not. If c comes out to be a function of a, then that means it depends on the rotation, so it is not objective. However, if c does not depend on a, then it is objective. So let's check that. So c prime ab as defined is f transpose f, that becomes f prime ia times f prime ib, and f prime is written in terms of f like this. So now if we take this as the starting point, we know that aik times aij is basically writing a transpose a, so that becomes a delta kj followed by fka times fjb, and this becomes fja fjb. So in symbolic notation, I can write c prime as c, because this was CAB. So what we notice is that the quantity C, that is the Green's deformation tensor, does not depend on the observer's rotation. It stays the same. If the observer rotates, the observer still measures the same quantity, that is C. So C, the Green's deformation tensor, is objective tensor. So this is the idea of material frame indifference, which allows us to check whether the quantity or the measure is indifferent to material frame rotation or translation or not. So we also call this sometimes as a check for superposed rigid body motion. So the idea is that the observer in the spatial coordinate system has rotated. So we rotate the spatial coordinate system, also translate, but since the quantities usually filter out the translations, so we only talk about rotations in general. So for checking for objectivity, we always rotate our spatial coordinate system for the check. So as we just found out that F is not objective and C is objective. So I've highlighted that you have to rotate the spatial coordinate system. That is, you write your x prime as the orthogonal matrix A times x. The next principle we talk about is the principle of material symmetry. So this is different from the previous idea of objectivity. The idea here is that the responses must reflect the material's internal symmetries. So till now we haven't talked about the directional symmetry of a material. We just talked about the observer making a measurement who may be rotating. But now we talk about the symmetry due to the nature of the material. For example, if you have an isotropic material like a metal or glass, then the constitutive law should look the same in all directions. So if I have a sample which is kept like this and apply a cause, that is a strain in this direction, that results, let's say, in a response that is a stress overall. Now, if I choose to apply a strain in this direction, the same strain, let us say the same longitudinal strain, then it should generate the same stress sigma ij as a result because the material is isotropic. However, if I had a material which was anisotropic, for example, let's say wood, so this was isotropic by the way, and then I applied a strain which resulted in some stress sigma ij, and if I apply the same longitudinal strain, that will result in a different sigma ej, that is sigma ij prime here. And the reason is because wood, for example, may have a different response to this strain because of its grains orientation. And our choice of constitutive model, which basically relates the sigma to the epsilon, should also respect this material's symmetry. Now, in a more general sense, it could happen that the material may have a symmetric response in certain directions. So it may be the case that the material is symmetric in these and these directions. However, for applying a strain in any other direction, it may not show the same response. So we have to ensure that our constitutive model that we develop also respects this material symmetry. And as I just said, that anisotropic materials will not be symmetric or will be symmetric about certain special axes or planes. So our constitutive model will have to respect or incorporate that information. So for the case of linear elasticity, which we'll discuss in detail in the next lecture, sigma, that's the response, is written as a function of epsilon in this way. So we multiply a fourth order tensor C to epsilon to get sigma. So this fourth order tensor has 81 components in principle, and these components have the information about the material behavior. So if, for example, this material was isotropic, that is, it was symmetric in all directions, then if I transform my C through any rotation like this, I would get the same C back. And the reason for that is because since the material is isotropic, so the constitutive model, which is taken care of by this fourth order tensor C, has to be isotropic as well. So if you visually look at a fourth order tensor with some components, if you rotate the material axes in such a way so that they point in different directions, even then the C components would still look the same. And this, as again we'll see later, results in the quantityCijkl boiling down to just two independent constants. So let us give you a recipe for checking for material symmetry. So let's say you have an object in the reference configuration and we have certain coordinate system. Let's say O capital X1, capital X2, capital X3, and then we rotate our coordinate system to get O capital X1 prime, capital X2 prime and capital X3 prime. And if I calculate the quantity C in the OX1, X2, X3 coordinate, and I also calculate the quantity C in the OX1 prime, X2 prime, X3 prime coordinate system, then the relation between these two will depend on the material symmetry. Now in continuation to that, we discussed the idea about why the invariants of a quantity matter when talking about constitutive equations, and this idea is linked to the idea of material symmetry. So let us have the discussion in terms of the quantity C, which is actually the quantity that is used for finite deformations. As we just saw that C is objective, so it passes the objectivity test, that is, it does not depend on the rotation of the observer. So we can use this as a cause for developing a constitutive model for finite deformations. But the new issue here is the material symmetry we just talked about. So let us see how we incorporate the idea of material symmetry in this picture. And as we said that the constitutive laws must respect the symmetry of the material or the symmetry group of the material. So basically the material may not be completely anisotropic. It may be isotropic in certain directions like an orthotropic material. So this is checked. We already checked for the objectivity of C. And by the way, in this slide, I'm using a slightly different notation, that instead of the matrix A, I use the matrix Q because that is more standard in the literature. So Q is a standard notation. So capital Q is a standard notation for writing rotation orthogonal matrices. This SO3 basically means the standard orthogonal group in 3D. So this is a set of all the matrices possible which denote rotations in 3D. So it's the same as the matrix A that we've been talking about. So we calculated that the transformed C prime, or in this case C hat as we call it, is the same as C. So C is objective. So that is checked for that C is unchanged by the observer rotations. Now in terms of the material symmetry condition, we just said that for rotations like now we use R, which is also coming from the SO3 set. So this was my constitutive model. So if I apply the rotation transformation to the model, then we get a C prime as I told you, and that would be the same as this, in this case for isotropic materials, but the relation between these two will depend on the symmetry of the material. Now we come to the idea of the invariance here, that for the isotropy condition we have been talking about, S, which is our stress tensor, but for finite deformations we call or we use the Piola-Kirchhoff 2 stress tensor, which is also symmetric. S can depend on C through the constitutive model only through its invariants. That is, our constitutive model cannot contain the individual elements of C. Because in that case, what will happen is that depending on the rotation I give to the material coordinate system, my components of C will change because the components of C change for material rotations, although they are objective, so they don't change for spatial rotations. But you can check that if you rotate the material coordinate system, then C changes to a C prime. So since the components of C change if I rotate the material coordinate system in which the material exists in the reference configuration, then for an isotropic material, my constitutive model can only contain the invariants of C, because the invariants of C do not change by rotating my material coordinate system. So components ofCijkl, the constitutive tensor, should be invariants of CAB, not the components of CAB. So if these are the three invariants, then there's something called a representation theorem, which we are not discussing as a part of this course because that's more advanced idea, but I can write the theorem briefly. Let's write it here. That sigma tensor, which is written as a function of C tensor, or in this case it's actually an S, it's written as some coefficient alpha, which is a function of the three invariants I1, I2 and I3 times identity plus another coefficient beta, which also depends on the three invariants, times C plus gamma, which again depends on the three invariants, times C squared. So we notice here that the constitutive law depends on the invariants of C, not the components of C. So till now we've talked about the restriction on the choice of the constitutive model based on symmetry, the symmetry of the material and the symmetry based on observer rotation. Now we'll talk about the restrictions on constitutive models based on thermodynamics. So the first law of thermodynamics is already embedded in the field equations. So there's no restriction on the constitutive model or the equation based on the first law of thermodynamics. The second law of thermodynamics, which is about the entropy or the randomness of the universe or an isolated system increasing with time, provides a test of admissibility for a chosen constitutive law. So every law that clears the symmetry test, whether of frame rotation or of material symmetry, does not necessarily satisfy the test for the second law of thermodynamics. So any proposed law that we have must be checked against the Clausius-Duhem inequality, which is a form of the second law of thermodynamics, to rule out unphysical models in the choices. So let us look at the procedure we have to follow to check for the admissibility of constitutive models based on the second law of thermodynamics. So this procedure is called the Coleman-Knoll procedure. So first we pick up a form of the Clausius-Duhem inequality that we have stated here. So this form is based on the Helmholtz free energy psi, which is obtained from the standard form of the Clausius-Duhem inequality by combining that with the first law of thermodynamics. So what we do in this case is that we postulate constitutive forms for the functions Helmholtz free energy, the stress tensor sigma ij, and the heat flux vector qi in terms of chosen state variables, which could be epsilon, temperature, internal variables alpha m. Then we insert the choice of these constitutive models into the Clausius-Duhem inequality. And the equation that we get provides us with the restrictions such as these. So let's actually do the exercise and see what restrictions do we get. So this is our starting point. This is the Clausius-Duhem inequality in the modified form. So let us say we assume a very general form of the Helmholtz free energy. That is, the free energy depends on the strain, the temperature, and the internal variables as well. So when we take a material derivative of psi, that is, we get psi dot and multiply by rho, this is the expression we get from chain rule. Then we substitute this rho times psi dot that we have got into the Cauchy-Duhem inequality, and that gives us this form of the inequality, including the terms such as epsilon dot, t dot, and alpha dot. Now, since we know that epsilon dot is independent of t dot, which is independent of this term here, so what this means is that I could choose any epsilon dot and contradict this inequality. So I can choose epsilon dot in such a way so that this whole term becomes so small, so negative, that overall the left hand side contradicts that this is greater than or equal to 0. So the only way this inequality can be satisfied is by ensuring that this term is identically equal to 0. And this gives us the first restriction, that is, the stress tensor can be written as a derivative of a scalar function psi. And we say that stress is work conjugate to strain. Later in the discussion on elasticity, we will see that this scalar function is actually the work function. Now, with a very similar idea, we can make t dot very small, so that may result in the left hand side becoming smaller than 0. So to ensure that this inequality is always satisfied, we have to make sure that the coefficient of this t dot is equal to 0 identically. So that results in the second restriction, which gives us the relationship between entropy and free energy. And then the last term here has to be greater than or equal to 0. And this last term is basically a sum of thermal and mechanical dissipation. So the overall dissipation has to be greater than or equal to 0. Dissipation has to be positive. So let's take a situation where this term is 0, because this term includes the effect of history. So let us say for the material, there's no effect on the history of straining or loading. So all the constitutive laws are instantaneous in nature. So in that case, it's only this term. And if you recall your Fourier heat conduction law, where we write Qi as minus K gradient of temperature, so that means our constitutive model for heat flux must be consistent with the Fourier type of laws for heat conduction. So what we have seen is that the second law of thermodynamics provides some restrictions on the choices for the constitutive models. The chosen models must satisfy these restrictions, and only then they are admissible. Now we'll briefly talk about the type of models, or the mathematical form of models. So one is called the instantaneous, the rate type models, where the response, let's say stress in this case, it depends on strain rate, or temperatures at the same time t. So the stress at a given time depends on these causal functions at the same time t. However, we can also have history dependent laws, or integral laws, mathematically speaking, where our response, let's say stress in this case, depends on the strain rate, for example in this viscoelasticity case, as well as it depends on all previous times. So there's an integral here with a relaxation kernel G, which helps encode the memory of the strain rate into the constitutive model that we have here for sigma. So by choosing the form of G, we can take care of fading memory effects. That is, the weight of the previous strain rates can be controlled by controlling this convolution kernel G. So G is also sometimes known as the green function. And typically speaking, what you will see is that the recent strains or strain rates will be weighted more than the older strains or strain rates. So this is the memory fading effect. But nevertheless, there is an effect of strains or strain rates from previous times as well for the stress at the current state. So we'll talk more about viscoelasticity in a greater detail when we talk about viscous models in 2 lectures from now. And as I said, that we can incorporate the effect of history through internal variables, which are alpha m's, where the index m denotes the number of internal variables. So typically what we'll see is that the response function will be written as a tensor function of epsilon, or maybe temperature as well, and then some internal variables alpha m's. And the material derivative of alpha m's will be specified through some another function which depends on the strain and other internal variables as well. Just as a teaser, I present some situations where we use alpha m's, although we'll discuss this in more detail in this week. So for example, in the case of plasticity, we write the stress as some constitutive tensor of fourth order times the elastic strain, which basically is the overall strain that we have in the material minus the plastic part, which is because of the hardening that's happened in the material over time because of plastic deformation. So basically this is our internal variable alpha m, and we specify the material derivative of epsilon p dot, that is alpha m, in terms of some other functions and laws. In another case, for example in viscoelasticity, that will be discussed later when we talk about viscous type of models, we use the collection of these springs and dashpots. In fact, we can have models where we have multiple branches of these, which is typically called the Maxwell branches. So since in this case, Maxwell type models, we have branches which are arranged in a parallel fashion. So in parallel, the stress adds. So we have these sigma ij's, which are the different stresses in the different branches, and the overall stress is the sum of these sigma a's. So these sigma a's are written using the constitutive model for one branch, and the internal variables in this case can simply be sigma ij's or the stresses for separate branches. You can also have some hidden strains instead, and again these ideas we'll be discussing later. Third type of situation where we have historical effects in the constitutive model is in the case of damage. So we can have a variable d that takes care of the damage or the extent of damage that has happened to the material. Let us say in the case of fatigue, where micro cracks are resulting in the material getting damaged. So the stress for two different materials which have been damaged to a different extent would be different, but the same strain in that case. So d here becomes the internal variable that takes care of the history effects in damage. So this brings us to the end of this introductory lecture on constitutive modeling. Today we discussed about the need of constitutive laws or models mathematically and from a physical perspective. So from a mathematical perspective, we showed that it is because of the closure or the lack of the number of equations we have, we need some more equations. And from a physical perspective, we noticed that we need to incorporate the effect of material because different materials respond differently to the same stress or strain. Then we also discussed that these constitutive models cannot be arbitrary. They have to satisfy certain conditions. So one condition is that they must satisfy objectivity. That is, they should not depend on the observer's translation or rotation. And then we saw that the constitutive model should also satisfy some material symmetry conditions. That is, the chosen model should satisfy the material symmetry group. And then we discussed that these chosen models must not contradict the second law of thermodynamics. And we discussed the Coleman-Knoll procedure, which allows us to test for the admissibility of a chosen constitutive model based on the second law of thermodynamics. Finally, we mentioned that these laws need not be instantaneous. It can also depend on the history of loading, which is typically incorporated as internal variables in the constitutive model. So after establishing the principles which are required to test for admissibility of constitutive models, now we'll start talking about different kinds of models which are available in the market. In the next lecture, we'll talk about simple models which are used for modeling elastic solid materials. So thank you very much, and I will see you in the next lecture.